All right, so the next thing we're going to talk about is linear transformations and connect that to determinants as well. So let's look at linear transformations. All right, we're going to start with a theorem as well. We're going to do 2 by 2 and then 3 by 3. So here's our theorem. It says let T that goes from R2 to R2 be the linear transformation determined by a 2 by 2 matrix. We're going to call that matrix A. Okay, so A is the standard matrix of our transformation. If capital S is a parallelogram, in R2, then we can say the area of T of S. All right, so let's first, before I write all this out, what does this mean? Well, if this is our parallelogram and we apply the transformation, T of S is going to be the result. All right, so what is the area of the result after we have applied the transformation? All right, that can be given by the determinant of our transformation matrix A times the area of the original parallelogram S. So we take a parallelogram, transform it. The area of the transformed one is going to be the absolute value of the determinant of the matrix of the transformation times the area of the original parallelogram. All right, alternatively, we're going to do this for 3 by 3. Alternatively, we are going to let T from R3 to R3 be the linear transformation determined by a 3 by 3 matrix. Call it A. If capital S is a parallelepiped in R3, then we can actually figure out the volume of our transformed parallelepiped. So the volume of our transformed parallelepiped is given by the determinant of our matrix of our transformation times the volume of the original parallelepiped. So same result, just in different dimensions. Okay, let's look at an example of this. All right, so I'm going to introduce a little new notation. You don't have to really remember this, but I'm going to call T sub theta and let this be a matrix of a transformation. It's actually the rotation matrix. So it's cosine theta, negative sine theta, cosine theta. All right, and so you should know from one of the sections in your book that this rotates anything, so any vector theta radians counterclockwise. About the origin. So whatever you multiply this matrix by, that thing is going to be rotated. All right, so for example, let's say our theta was pi over 2, so 90-degree rotation. We got 0, 1. So if you cosine of pi over 2 is 0, sine of pi is 1, so this is going to be -1, and this is 0. And so this is a pi over 2 rotation. All right, so what if we apply this rotation to a parallelogram, the same one we worked on earlier? All right, so let's do this rotation. This is our parallelogram from a long time ago. You can't see that. All right, so this is the B I'm talking about. So we're going to take this parallelogram and we are going to rotate it counterclockwise 90 degrees. Well, how would we do that? Well, all we have to do is matrix multiply. Transformation times our parallelogram. All right, so this result is going to be our parallelogram. After it's been rotated pi over 2 counterclockwise about the origin. All right, so this is our transformation matrix. This is our original parallelogram. So when we transform our parallelogram, it just gets rotated. So now let's bring it back to the theorem. What if I just wanted to figure out the area of this new parallelogram? All right, to do that, I would take the absolute value of the determinant of this thing. So I'm just going to do 0, 1, -1, 0. Absolute value of the determinant times the area of our original B. All right, so this one is just 1, and the area we found in our previous problem area of parallelogram is 15. So that means the area of our new parallelogram is 15. Does it make sense that this new parallelogram has the same area It should, because all we did was rotate it. We didn't stretch it, we didn't shrink it, we just turned it. All right, so if this were a different transformation that scaled it, of course our area would be different. All right, so this is the same as the original because we only rotated it. All right, so that is the end of this section.